Now let's look at how to sketch a function from a verbal description. The incidence of a disease is the rate at which a disease occurs in a population. It is calculated by dividing the number of new cases of a disease in a given period by the size of the population. To avoid small decimal numbers, the rate is often expressed in terms of a large number of people rather than a single person. For instance, the incidence of measles in the US in 1974 was about 10 cases per 100,000 people. Okay, now we are going to use that information and the following paragraph to sketch out a graph on the incidences of measles in the US according to time and cases in the population. Okay, so you kind of have to follow along and look at the information provided as to how to start, how your chart is going to look, whether you go up or down, right, left or right. You have to read the description and you have to follow those descriptions. So first thing I'm going to point out is that we know in 1974 we had 10 cases per 100,000 people. That's our starting point, okay? Now, the following paragraph says from 1974 to 1980, there were drastic fluctuations in the incidence of measles in the US. In 1975, there was a slight increase in incidence from 1974. The next 2 years saw a substantial increase in the incidence, which reached a maximum in 1977 of about 26 cases per 100,000 people. From 1977 to 1979, the incidence fell to about 5 cases per 100,000 people, and the incidence fell much faster from 1977 to 1978 than from 78 to 79. Finally, from 79 to 80, the incidence stayed about the same. Sketch a graph of the function for the incidence of measles. So if you look at your graph, this is based on time since 1974. So one would be 1975, 76, 77, and so on. And then we have the cases per 100,000 people, okay? So we are sketching a graph that ranges from 74 to 80. That's a span of 6 years. So we know we're going to end somewhere on 6, right? That's going to be our terminating point when x is 6. Our starting point, we already said in 1974, so at 0, we had 10 cases. That's our starting point. In 1975, there was a slight increase from 74. So slight means not that big, so we're going to draw a small line, right, with barely a slope to it. And then it says the next 2 years saw a substantial increase. That means that there is a big increase, which reached a maximum in 1977 of about 26 cases. So 1977 is 3 years after 1974, and we have a maximum of 26. I know there's going to be a turning point here, and we can see that substantial increase from 75 to 77, the next 2 years. Okay, there's our substantial increase. And then we go from 77 to 79, the incidence fell to about 5 cases per 100,000. So in 1979, it's been 5 years since 74. So at 5, right, this is where it fell. Here's our point. We can connect those 2 points. We have a second part of our graph. And then finally, from 79 to 80, which is 1 year, the incidence stayed about the same. That means a horizontal line because there was no change in the cases. Okay, now it's not going to be a perfect graph, right? We drew out our points. We drew out the coordinate points that we did know, which were 3. And then we based our slope or our rate of change based off of the descriptions we were reading, okay, which aren't a lot. We had that slight increase in 1 year. We had the substantial increase the next 2 years. We had that dramatic decrease the following 2 years, and then it stayed the same. Okay, so this is what the sketch of the graph would look like. Now, the reflection question says the graph is horizontal from 79 to 80. What can you say about the rate of change for the function of interval? Well, because our line is horizontal, our rate of change is 0. There is no change. It stayed the same, which tells us that our graph is constant. Okay? There is no change, there is no decrease or decrease in the measles, in the incidence of measles. So our graph is constant. It's going to stay. We can simply rely on it staying the same. Okay. All right. So again, hit the pause button. Try the next example. Graph out the graph for strawberries on shelves. All right, this is what your graph should look like, and this should have been substantially easier to do than the first example we did. First of all, it tells you that the grocery store is stocked with 100 cartons of strawberries. That's your starting point, y-intercept 0, 100. For the first 3 hours the store is open, the store sells 20 cartons per hour. So you can easily go down the first hour minus 20, second hour minus 20, third hour minus 20, and you can see that I have those points for each of those 3 hours. Over the next 2 hours, no cartons are sold. So that means we still have 40 cartons in the store at the 5-hour mark. The store then restocks 10 cartons each hour for the next 2 hours. So plus 10 for 1 hour, plus 10 for the second hour. And in the final hour, 30 cartons are sold. We subtract those 30 cartons in the last hour, and you can see that at 8 hours we have a total of 30 cartons left over. Okay, so when you have that much detail, it's very simple for you to simply plot the points and then come back and sketch your line, right? And remember, do it as straight as possible. And I know it's hard if you don't have graph paper, but just do your best. And this would be your graph for the sale of strawberries.